In this video, I like to talk about Fourier sine and cosine integral formulas. And this is actually rather simple to do as well. Look back again at the Fourier integral representation formula 8.2, where f can be written as a Fourier integral with the coefficients capital A of omega and capital B of omega. Now, if the function f would be even, let's say if f is even, okay, so then here f would be even, cosine is also an even function. So then instead of an integral from minus to plus infinity, we can also write this as an integral from 0 to infinity, but then we get the same thing twice. All right. If f is even here and the sine is odd, then the whole function would be an odd function, which we integrate over a symmetric domain, so the integral would then immediately be 0. So if f is even, okay, the b is 0, is gone, and what we keep is a pure cosine integral formula for f. Okay, keep that in mind. F even, you get a cosine integral formula. What happens if f is odd? Weedy. So if f is odd, okay, then this guy here would be odd in the coefficient a. Cosine is even. Together it's an odd function. Integrated from minus to plus infinity is 0. The first term is gone and we get a pure sine integral. So then f odd means we get a sine integral. Keep that in mind. If the function f is defined on 0 to infinity, then we have again two possibilities, right? We can make the even extension or the odd extension. F even on minus to plus infinity, or f odd on minus to plus infinity. And as I just argued, if I use the even function, then I get a pure cosine integral. If I use the odd extension, I get a sine integral. So that's what's happened here on the next page. So here's the cosine integral. First of all, I need finite mass, same condition as before. We only integrate now from 0 to infinity because this is where f is defined. But then we can write f as a cosine integral by using the even extension in the coefficient. And if I use the even extension, then f is even, cosine is even, so I get the additional 2. Same argument I talked about earlier, okay? So if we start with a function from 0 to infinity, we use the even extension, we get the cosine integral. And guess what? If we use the odd extension, we get the sine, okay? So here's the odd extension, becomes a coefficient in the sine integral for f. And then here f is odd, sine is odd as well. So we can do the same trick by changing the integral from 0 to infinity, but then getting it twice. Good, so that's that. Let's look at this little example again. F is 1 between 0 and 1, and it is 0 for x is bigger than 1. So then this f would be this function here, and jumping to a half. Here is 1, here is x. Okay, and so then for the cosine integral, we look at the even extension, which is exactly the function we had before. And for the sine integral, we look at the odd extension. So that's the function here, and the odd extension goes then down there. So that's what we have to do, all right? So then here for the cosine integral, here it's in formulas. Yeah, we can just use the formula from before, and we get 2 over pi sine omega divided by omega. That's exactly the same integral we solved earlier. And for the odd extension here, we then get the integral with the sine, f with the sine. And so you integrate sine and you get cosine, subbing in 1 and 0. So you get 2 over pi omega 1 minus cosine omega. So this goes right here. And then we have the representation using the sine.